Almost every time there's a big announcement in astronomy, you hear of them using telescopes in really sunny places, like the Mauna Kea Observatory in Hawaii and the Paranal Observatory in Chile. And if it doesn't come from there, then it comes from space. But how did astronomers manage to get all of their big fancy telescopes built in such sunny locations? Doesn't this all seem a little suspect? Well, my name's Thomas, you're watching Inversion Science, and this is the real reason telescopes are built in sunny places. Now, not all telescopes are built in places like Hawaii and Chile. There are a good number of space telescopes, such as NASA's Hubble Space Telescope, the endlessly delayed James Webb Space Telescope, and the European Space Agency's Cheops Planet Hunting Telescope. And there are astronomical telescopes all over the world, with many universities operating their own, such as the James Gregory Telescope at the University of St Andrews. But while these telescopes all do really good science, they aren't where most of the investment goes these days. These days, with scientists trying to probe deeper and deeper into the cosmos, and trying to detect fainter and fainter signals, and with the endless delays to space telescopes like the James Webb, it becomes clear we have to build telescopes in the best possible locations here on planet Earth. Places with glorious sunshine, like Hawaii and Arizona. So, clearly that means we all want to go on a holiday, right? And while I'm sure it is nice to get expense-paid trips to Hawaii on grant money, the real reason that we build telescopes in these places is far less suspicious. Our problem is the atmosphere. Now, before I go hating on the atmosphere for screwing up astronomy, I will admit it's pretty good. It's pretty great, actually. And I really wish humanity would stop screwing it up. If we had no atmosphere, the surface of the Earth would be more like the surface of the Moon, where at the equator the temperatures can get as high as 120 degrees Celsius during the day, and at night they plummet to minus 150. At the poles it's even worse, where at night the temperatures get as low as minus 250 degrees Celsius. The bottom line is, without the atmosphere, we have no life, and I'm not here to complain about the atmosphere screwing with astronomy. But the atmosphere isn't this nice, static, life-sustaining bubble around the Earth. It moves, it's turbulent, and this turbulence is what causes the problems for astronomers. This turbulence in the atmosphere causes what astronomers call seeing. Seeing is what we call the blurring that the atmosphere causes. It's what makes stars twinkle. When light passes through the air, it's not like passing through space. In space, there is very little to cause light to spread out or to change its path. In the atmosphere, that's not the case. Now, if you've done any physics in high school, you've probably heard of something called the Refractive Index. Normally we talk about this when light goes through glass. When light passes through a medium like air or glass, it is slowed down, and its path can be altered. The denser the material, generally the higher the refractive index. Since the atmosphere isn't static, we get pockets of higher density. These higher density pockets can be incredibly localized, which leads to minor changes in the refractive index in a very small area of the atmosphere. These differences in refractive index can make the once smooth wavefronts of light sort of bent out of shape, causing seeing. While we're in atmosphere, there will always be some amount of seeing to deal with. On a good night in St Andrews at sea level, the seeing can be approximately 2 arc seconds. And while that doesn't seem like very much, it can be a lot better at the best astronomical sites in the world, where the seeing is as low as 0.5 arc seconds. These sites are, oddly enough, where we've built a load of telescopes. But doesn't it all seem a bit convenient? The best places in the world to build telescopes just happen to be holiday destinations? What makes them so good for astronomy? Well, the reason we build telescopes in places like Hawaii or Chile falls down to 2 main factors. The first is that Mauna Kea in Hawaii and Cerro Paranal in Chile are really high. The observatory on Mauna Kea is 4.2 kilometers above sea level, and the observatory at Paranal is 2.6 kilometers above sea level. This gets the telescopes above a lot of the clouds and cuts out a lot of the atmosphere, which telescopes like the James Gregory at sea level really need to deal with, and it causes a lot more blurring, increasing the seeing. But building telescopes up mountains for a 1.5 arc second improvement in seeing? That seems like a lot of effort for not much gain. Surely it would be cheaper to just build more telescopes at lower altitudes and do more observations. Well, the reason we build telescopes up mountains where the seeing is only 0.5 arc seconds is because of technologies that allow us to compensate for the seeing. All telescopes have what is known as a diffraction limit. This is the limit of the optics of the telescope. It's not something we can bypass with the technology. But the only optical telescopes that are ever truly limited by this are in space, where they have no atmosphere to cause seeing. But it is worth noting that radio telescopes on Earth are diffraction limited, because their diffraction limit is actually greater than the atmospheric seeing. The goal of any optical telescope observation is to get as close to the diffraction limit as it's possible to get. This is achieved using technologies collectively known as adaptive optics. Adaptive optics analyse the image being taken during the observation and then deform the mirror of the telescope to account for the seeing. The easiest way to do this is to use a bright star within the field of view of the telescope that isn't the target of the observation. The system determines what it needs to do to restore this bright star to a point source, and then uses those adjustments to improve the entire image. Unfortunately, there aren't nice bright stars in every bit of the sky, so sometimes we have to improvise. What we do now is way cooler. We use lasers. Specifically, we create what is called a laser guide star. This is laser light backscattered off sodium atoms in the atmosphere. The adaptive optics system then treats it like the bright star from before, using backscattered light to extrapolate the seeing effects for the entire image and improve it. Now, while adaptive optics is really useful, it's not a magic bullet that fixes everything. We could use it on the James Gregory telescope, but it wouldn't work in the same way that it would for the Keck Observatory at Mauna Kea. Adaptive optics isn't powerful enough to compensate for the full 2 arc seconds of seeing in St Andrews, but it can get a lot closer to the diffraction limits of the telescopes at Mauna Kea, because the 0.5 arc seconds of seeing is much less to deal with, meaning we can deal with a much larger proportion of it. So if it's so good to put telescopes up mountains, why haven't we put any at the top of Everest? Surely that would cut out the most atmosphere. And while that is true, it would get through a lot more of the atmosphere. It's really damn hard to climb Everest. Not to mention the fact that it's really inland. Mountains like Mauna Kea are more solitary peaks. Hawaii is surrounded by miles and miles of ocean, while Everest is far inland among the Himalaya mountain range. The Himalayas cause the air to be whipped up and becomes more turbulent, whereas Mauna Kea, surrounded by miles and miles of ocean, has nothing to break up the air. That means that by the time the air has flowed towards Mauna Kea, it's much smoother, it's laminar. Laminar airflow is much less turbulent, so it improves the seeing at a given site. This is something that we wouldn't get at Mount Everest, where it's surrounded by other mountains. Laminar airflow is mostly found near the coast, which is why the airflow at Mauna Kea and at Cerro Paranal are just so much better. So no, astronomers have not managed to pull off some multi-decade con to get holidays paid for by grant money. Telescopes are built in places like Hawaii not for the holiday locales and the nice beaches, but because they actually produce better data. The science that can be done in places like Mauna Kea and Paranal are just much more useful and cost effective. So if you found this dive into why we put telescopes where we put them, then please hit that like button and subscribe for more videos like this. If you're looking for something else to watch, I would highly recommend my recent video on how it's possible for us to see behind black holes. You can find the sources for this video linked in the blog post in the video description, and while you're down there, if you have any comments, criticisms, or video suggestions, then please leave them in the comment section. Until next time, I've been Thomas, you've been watching Inversion Science, and I'll see you in my next video.